Hi everybody, today I'm going to explain the fourth Fulkerson algorithm and its usage to find the max flow, the min ST cut, the maximum bipartite matching, and the min cost max flow, which uses a cycle cancelling algorithm. You can find the source code, the Java code for all this on my website www.algos.org. Right, let me start by explaining the max flow. Before that, if you know about the max flow and you're interested in the other algorithms, you can just jump straight in to that section of this video. I've updated the start times of all algorithms in the description section of this YouTube video. Let's start by explaining what a flow network is. A flow network is a graph which has two special nodes, S and T. S stands for the source and T the sink. The source is which the flow originates or enters the network, and T is the sink from which the flow dissipates or goes out of the network. Then we have multiple intermediate nodes like A and B. Then we have edges which connect these nodes. These edges have capacities. These are the max capacities. No flow along that edge can exceed its capacity. We denote Cij as an edge as a capacity along the edge ij. Now supposing we know what the max flow along this network is, what questions can we answer? Now let's assume S and T are two cities, A and B are some intermediate cities, and this is a road network between these cities S and T, with the edges being the roads and the capacities being the max traffic along this road. So if we know what the max flow is, we can answer questions like what is the max traffic this road network can support, and which roads are the bottleneck roads if we need to increase the traffic capacity. For example, A and B, the road between A and B is of a min capacity. If we need to increase the capacity along this entire road network, we need to modify this road to increase capacity or add additional roads between A and B. Maximum flow. Here we seek the total maximum flow from S to T given the edge capacity constraints of G. Cij denotes the capacity at edge ij and xij the flow to directed edge ij. The first constraint is known as the capacity constraint. What it means is that xij should be greater than equal to 0 and should be less than equal to capacity Cij. That means the flow across the edge should not exceed its capacity nor should be less than 0. Furthermore, an equal flow comes in as goes out at each non-source or sink vertex. It's known as a conservation constraint, which states that for all intermediate vertices, the incoming flow should be equal to the outgoing flow. Now we seek the assignment that maximizes the flow into sink T, namely maximize summation I is equal to 1 to n xit. Of all the flows, we seek the maximum flow. Now before we go into the fourth Fulkerson algorithm, we should understand two different concepts. One of them is augmenting path, which is the path from S to T on the graph where no vertices are repeated and no edge along this path has its capacity saturated. For example, in this graph below, S to A and A to T is a path from S to T. No vertices are repeated and no edge along this path has its capacity which is equal to 0 or less than 0. The next concept is residual graph. Given a flow network G and a flow F on G, we define the residual graph GF of G with respect to flow F as follows. 1. The node set of GF is the same as that of G. 2. Each edge E equal to UB of GF is with the capacity of CE minus FE. C is the capacity along the edge and F is the flow along that edge. That means you subtract the flow from the capacity along the forward edges. This is known as the residual capacity. 3. Each edge E dash equal to VU of GF is with capacity of FE. E dash VU is the reverse edge of UV. For the reverse edges, we keep the capacity equal to the flow along the forward edges. Now let's assume there is a flow of 1 from S to T along the edges S to A to T. According to residual graph definition, we subtract the flow F of 1 from the forward edges. So 2 will become 1, 3 will become 2. And we add reverse edges T to A with equal to a residual capacity equal to flow of 1. T to A and A to S. S to A to T reduced by the flow 1, and T to A is equal to the flow, A to S is equal to the flow. This is the residual graph for the flow of 1 along these S to A to T edges. Let's go to the actual pseudocode of Fulkerson. 1. While exists an augmenting path P, push maximum possible flow along P, saturating at least one edge on it. Call this flow FP. Now maximum possible flow along P is the same as the minimum capacity along any edge along this path. So if you're pushing that much flow, we're actually saturating that minimum capacity edge. Then B. Update the residual graph, that is subtract FP on the forward edges and add FP on the reverse edges. That's the definition of residual graph. C. Increase the value of the variable max flow by FP. Now we do all these three steps until we cannot find any more augmenting paths. Then 2. The flow in variable max flow is the maximum flow along the network. Now the complexity. The runtime of Fulkerson is bounded by big O Fe, where F is the maximum flow in the graph and E is the number of edges in the graph. As each augmenting path can be found in OE time using DFS, that is depth first search algorithm. Second, the upper bound and number of times to find an augmenting path is F, max flow, as in every path we can increase the flow by at least 1. Now the worst case is that in every augmenting path we can increase the maximum possible flow equal to 1. So total number of times we need to find an augmenting path is equal to F, which is the max flow. So maximum times you need to run DFS is Fe, which is the upper bound known as OFE. Now the proof of correctness of the Fulkerson max flow algorithm. I'm not going to give the actual proof here. I'm going to show you the 3 lemmas that need to be proven. The first lemma is every augmenting path is a valid flow. Augmenting path satisfies the capacity constraint, and the actual pseudocode of the Fulkerson also satisfies the conservation constraint. Second, the algorithm is finite. Each augmenting path increases the flow by at least 1, so it's finite. 3. The flow found is maximum. Now it depends on something called as the max flow min cut duality theorem. A. For any flow F and any ST cut, F is less than or equal to the capacity in ST cut. An ST cut is a cut which separates the vertices into two disjoint sets. No edge is common between any two sets, between these two sets. And to form an ST cut, we need to remove some edges. Now the capacity of this cut or an ST cut is equal to the sum of the capacities of the edges we removed. Any flow F and any ST cut, F should always be less than capacity of an ST cut. B. We cannot find an augmenting path if the edges in any cut are saturated. So the algorithm actually finds an ST cut. C. Therefore, the F flow found in the fourth Fulkerson is less than or equal to any capacity of ST cut. But it is also equal to a capacity of some ST cut. Therefore, F is equal to max flow. Figure 1 shows a graph from which we need to find the max flow. First, the first step in the algorithm is finding an augmenting path. We can see an augmenting path along S to A to B, and B to T. Now we need to pass the maximum possible flow along that path. S to A to B, B to T, the maximum possible flow is 20. So we need to create a residual graph for this flow. Figure 2 shows a residual graph. For example, S to A, we are decrementing 40. We are decrementing 20 from 40. So remains 20. The residual capacity is 20. And we add a reverse edge from A to S, which is equal to the flow, which is 20. Similarly from A to B and B to T. And B to T, 20 minus 20 along the forward edge is 0. We do not show edges which have capacity 0. Reverse edge is equal to the flow 20. So figure 2 is the residual graph for this particular augmenting path. Now we find another augmenting path, S to C, C to D, and D to T, again with flow 20. We create a residual graph for it. Figure 3 is a residual graph for that. C to S, there's only a reverse edge of capacity 20. Now what you have seen is that we have added two augmenting paths. Sorry. We added two augmenting paths, both of value 20. So the total flow coming in into T is 40. Now we see for another augmenting path. There is another augmenting path from S to A to C, C to D, and D to T. Now here is with the flow here is 10. So we create a residual graph for that. This is a residual graph for this particular augmenting path of 10. So total flow has increased from 40 to 50. And we can see that we cannot find any more augmenting paths. Those are the paths from S to A. There is no path from S to T. S to A to B, there is no path from B to T. Similarly, there is no path from S to C. So there are no more augmenting paths within this graph. So this is the final residual graph. And the max flow is 50. Now, we can also find the actual flow to this graph. What you need to do is, for all the reverse edges, we need to reverse all the reverse edges, we need to make them as forward edges. The forward edges, we need to remove them. This is as shown in figure 5. For example, S to A, it was a reverse edge in figure 4, in the residual graph 4. We made it as a forward edge. Similarly, A to B and B to T. So now the actual flow is 30 along S to A and 20 along S to C, and so on. The max flow is total flow entering T, that is from B to T is 20 and D to T is 30. Now given the residual graph with back edges in figure 4, it can also be used to find the min ST cut and the min cost max flow. Now in the previous example, I've shown the residual graph, but we haven't actually used it to find augmenting paths. Now in this example, I'll show you how the reverse edges can be used to find extra augmenting paths. It all depends on which augmenting path you select. Now let's say we selected augmenting path S to A to T with flow 10. And then we select S to B, B to T, again with flow 10. S to A to B, A to T, flow 10. S to B, B to T with flow 10. So the total flow is 20 along these two augmenting paths. There are no more augmenting paths. So this is the max flow. Now let's see what happens if we selected an alternate augmenting path. Say S to A to B, B to T. We select S to A to B, B to T. Flow along it is 10. The flow coming into T is 10. Now can we find any more augmenting paths? We see that we cannot find, because here the capacity was 10, the flow along it is 10. So we cannot find an augmenting path because this edge is saturated. Similarly, A to B is saturated, B to T is saturated. Now S to B is not saturated, the flow is 0, capacity is 10, but there are no paths from S to B, B to T. So this is where residual graph comes into picture. Let's do a residual graph for it. Now we have reverse edges with residual capacity equal to the flow. A to S, B to A, and T to B. Now are there any paths, augmenting paths now? We can see if you take a reverse edge as one of the edges in the augmenting path, there is an augmenting path S to B, B to A, and A to T with capacity equal to 10. So we create a residual graph for this flow. Now what happens for this reverse edge? This reverse edge from B to A is a residual capacity 10. Now we subtract the flow of 10. So now, and we add the flow along the reverse edge from A to B. The reverse edge is the same as the forward edge in the original graph. So now the original edge has come back, the reverse edge has disappeared. What is the flow now? Now since we added two augmenting paths, S to A, A to B, B to T, and S to B, B to A, A to T, both with flows of 10, the total flow equal to 20, which is actually the max flow. Now to find the min ST cut using a fourth Fulkerson algorithm. The definition of an ST cut. In a flow network, an ST cut is a set of edges whose removal disconnects S, which is the source, from T, the sink. Or formally, a cut is a partition of vertex set into A and B, where S is in A and T is in B. The edges of the cut are then all edges going from A to B. The capacity of an ST cut is defined by the sum of the capacity of each edge in the cut set. The min ST cut is the minimum of all ST cuts. After the definition, let's go for the actual theorem using the fourth Fulkerson algorithm. Now the max flow min cut duality theorem states that in any graph, max flow from S to T is equal to capacity of min ST cut. So once you know the max flow, we know the capacity of an ST cut. To actually find the edges in one of the min ST cuts, we need to go further. First find the max flow residual graph GF V, EF using fourth Fulkerson algorithm on graph GVE. The max flow is the min ST cut. Second, find set of vertices which are connected from source S in GF, call the set A. Then find the edges going from set A to set V minus A in original graph GV, E. These edges form the min ST cut. Let's show this by an example. Min ST cut using residual graphs. On the left hand side is the original graph G. On the right hand side is the residual graph GF of max flow 50 in G. This is found using fourth Fulkerson algorithm. Now we go one step further. We find all the vertices which are connected from source S in the residual graph. All the vertices which are connected from source S. S, A, B, C isn't connected, D isn't connected, T isn't connected. S to A to B. This forms set A. As you see, S to C isn't connected. There is no path from S to C. Similarly, there is no path from S to D. And there is no path from S to T. So C, D, T form the set V minus A. And S, A, B form the set A. According to the algorithm, we have to find edges which actually connect set A to set V minus A, but in the original graph G. This is set A. Now B to T is an edge from set A to set V minus A, which is found in the original graph G. Its capacity is 20. Similarly, there is an edge A to C. Finally, there is an edge from S to C. C to D, which is there in the original graph, is not included in this because it's not going from set A to set V minus A. It's in fact going from set V minus A to itself. So these are the only three edges we need to be removed. And the capacity of the ST cut is equal to 20, 10, 20 is equal to 50, which is the max flow, according to the max flow min cut theorem. So vertices coming from set A to set V minus A in GV, edges are ST, SC, AC and BT. These are the cut set edges whose sum will equal to the max flow 50. This is how you find the min ST cut using residual graph found from fourth Fulkerson algorithm. Now we need to find the maximum matching in a bipartite graph using fourth Fulkerson algorithm. A bipartite graph defined is a set of vertices in graph G, V, E, which can be partitioned into two disjoint sets M and N, so that no two vertices in the same set are adjacent. That is, every edge E belonging to E has one endpoint in M and the other endpoint in N. Now there are two disjoint sets, no vertices are common between these sets, and no edge is there between two vertices of the same set, and every edge has one endpoint in M, the other endpoint in N. Now a matching. A matching is a set of edges with no endpoints in common. In bipartite graph, matching is a set of edges with no endpoints in common and with one endpoint in set M and the other in set N. Now this is a bipartite graph, figure 1. But this is not a matching because these two edges have one endpoint in common. However, in figure 2, this is a matching. There is no edge which is common, which has a common endpoint. Also, the definition of a maximum matching is if any edge is added to it, it is no longer a matching. Now, the applications of max bipartite matching. One of the many applications. Yeah, there are job applicants and n job. Each applicant has a subset of job that he or she is interested in. Each job opening can only accept one applicant, and a job applicant can be appointed for only one job. Find an assignment of jobs to applicant in such that as many applicants as possible get jobs. The second of the many applications are in scheduling problems, such as assigning m jobs to a machine with n time slots, with constraint certain jobs can be performed only during some particular time slots. What is the maximum number of jobs that can be performed in a day? This is a complicated version of max bipartite matching. Now, using Fulkerson to find max bipartite matching, the algorithm. The create vertices S and T. These are source and sink vertices. Connect S to all vertices in left set M. These are directed edges from the source to the all vertices in left set M. Similarly, connect all vertices in right set N to T. Give each edge in this graph a capacity 1. Find the max flow from S to T using Fulkerson. Output the matching corresponding to flow. For all edges from N to N, reversing these edges will give the maximum matching edge set. Now the maximum flow, the maximum number of vertices which are matched from in set M and N is equal to the max flow. And to get the edges or to get the matching corresponding to one particular maximum matching, all you need to do is reverse the edges from N to N to N to M, and you'll get the maximum matching edge set. This is this graph is a bipartite graph. We need to find the maximum matching in this graph. So first we need to add the source and sink vertices. We add the source and sink vertices. From the source we add directed edges to all vertices in the left set. Left set has all caps as vertex labels. And then similarly from the right set we add edges towards the sink. We give all of them a capacity as 1. Then we start with the actual Fulkerson algorithm. We need to find an augmenting path. There's an augmenting path from S to A to A to T. S to caps A to small a to T. So we need to create a residual graph for it. Now we don't need to add capacities because all we need to do to create a residual graph is remove the forward edge and replace it with the reverse edge. For this particular augmenting path, we remove the forward edge and replace it with the reverse edge. So this is a residual graph for this flow. Now, are there any more augmenting paths? This is an augmenting path from S to B, S to B, B to A. However, we are using one of the reverse edges, A to A to B, and B to T. So we need to create a residual graph for it, remove the forward edges, and replace it with the reverse edges. Are there any more augmenting paths? This is an augmenting path from S to C, C to C, and C to T. So we create a residual graph for it. We can see now that there are no more augmenting paths from S to T. So this is a final matching. The total vertices which are matched is equal to the max flow, which is equal to 3 here. And to find the actual matching, all we need to do is go to the reverse edges. There is a matching from A to B, caps A to small b, because it's a reverse edge from small b to caps A. So A to B, B to A is matched, and C to C is matched. So the max bipartite matching, A to B, B to A, C to C. There is no matching for D, however. This is one of the particular bipartite matching depending on which augmenting path we selected. So the total maximum matching will be same, but which of these edges will be matched depends on which augmenting path we select. We have to find the min cost flow, max flow using Fulkerson. The min cost flow is the max flow with minimum cost. The mean cost network has three different nodes. One is the supply nodes, demand nodes, and transshipment nodes. They can be multiple nodes of the same type. For example, in this graph, which is a min cost flow graph, we have S1 and S2, which are supply nodes. Supply nodes are like factories which can produce goods. Then the T1, T2 are demand nodes. These demand nodes are like markets where goods are sold. So there's a particular demand for some goods in this node. So T1, T2 are demand nodes, while A and B are transshipment nodes, or also known as warehouses. Then we have edges which connect these nodes. These edges have two values. This is Uij, Cij. Here Uij represents the capacity because we are only using Cij for the cost. Cij is the unit cost. So what here 7,3 means that to transport goods from S1 to A, the cost would be 3 per unit, and the maximum goods number of goods you can transport across this edge is 7 units. Apart from these edges and the edge labels, we have other labels like B is equal to 3 for source for each vertex. In fact, so if it here B is equal to 3 means that S1 can supply 3 units of a particular good. S2 B is equal to 7 means S2 can supply 7 units. T1 can supply T1 has a demand for 4 units. This negative is just a convention. T2 has demand for 6 units. So the formula convention here is written as Bx is greater than 0, it's a supply node. So node X can supply Bx units. By is less than 0, it's a demand node. Node Y has a demand of By units. Bz equals to 0, that means it's a transshipment node or warehouse nodes. Cij is a unit cost, Uij is a capacity, Xij is flow. So the aim here is to minimize the total cost Cij, Xij across all edges. The summation, the total flow cost should be minimum. Subject to additional constraint that the Xij, the flow across the forward edge minus flow across the reverse edge, flow across the incoming edge minus flow across the outgoing edge should be equal to the Bi value. For transshipment nodes, the Bi value is always 0, so the flow coming into the vertex should be the same amount of flow going out of it, and so on. This should be for all edges in the graph. So the min cost flow problem can be restated as: find all the feasible maximal flows to the graph G. Find the minimum of these maximal flows in terms of flow cost. Now the pseudocode for finding the min cost flow. So find a feasible maximal flow in graph G using Fulkerson. Now, since there are multiples, there can be multiple source and sink vertices, and then there are, B values associated. We need to first chain this min cost flow network into a normal flow network. Then you find the feasible maximum flow along in that graph G. Then create a cost network. So there's two. Create a cost network GC of the residual graph GF. For all edges FU belonging to GF, if edge UV belongs to G, then cost C FUV equal to CUV in GC. That is, if for all the forward edges in the residual graph, we keep the cost as is. We remove the weights, and we replace them by costs. For the forward edges, we keep the cost as is. For the reverse edges, else CFUV is equal to minus CUV in GC. So in the cost network, the reverse edge will have actually the weight equal to negative cost for the forward edge. So now we are going to find a negative cost cycle used on the cost network. If we find a negative cost cycle using Bellman-Ford, which is reachable from sink T, if we can find a negative cost cycle, then we remove the negative cost cycle by increasing the flow along each directed edge UV in C by the bottleneck capacity in the cycle C. This is like how we augment the flow. Now again we go to step 2. We create a cost network again and see if there are any more negative cost cycles. If there are no more negative cost cycles, then calculate and return the sum of the total cost into flow along each edge of the flow in residual graph. So now the cost is equal to the cost of per unit into flow along that edge. So the important thing is here is after finding a feasible maximum flow, we need to remove negative cost cycles. And before that, to find the feasible maximum flow, we need to actually transform this min cost flow graph into a a normal flow graph. What are the dissimilarities of a feasible flow in min cost flow in a flow network? If you remove the costs, the similarities are the capacity constraints and the flow conservation constraint. And as in residual graph, FUV should be equal to minus FVU. The dissimilarities are the min cost flow graph can have multiple source sink supply demand nodes, while the flow network has only one of each. And second, most importantly, the outgoing flow from each source SU has a strict bound, while in the flow network, the source could produce as much flow as possible. But here, it has a strict bound. It cannot be less than that. It cannot be more than the BU value. Similarly, incoming flow to each destination DU has a strict bound DU. These are the similarities and dissimilarities. Now, how do you transform a min-cost flow network into a flow network? Now in the first figure, the top figure is a graph which is a min-cost flow. It has supply nodes S1, S2, demand nodes T1, T2, intermediate or transshipment nodes A and B. It has the B values B is equal to 3, B equals 7, minus 4, and minus 6. Now to transform this into a network flow network graph, we need to add a super node, super source, and a super sink S0, T0. And we need to add edges from the super source to all the sources in the cost graph equal to the value of its with the capacity value equal to the value of its B value. So now from S0 we need add an edge to S1, and the capacity of this new edge is equal to the B value is 3. Similarly from S0 to S2 the capacity value is 7, we put 7 here. Similarly from T1 we add an edge to the sink T2 T0. Similarly from T2 T0 value is 4, B value is minus 4, here it's negated and made as 4, and similarly minus 6 negated and add the value 6. Next, the second important thing about in the algorithm are finding a negative cost cycle. Now what are negative cost cycles and how do they affect the min cost flow? Let's say this in figure 1 is an original graph. It's an original min cost flow network graph. So it has here it has one supply node and one demand node. Now in figure 2 is a residual graph for the max flow. See if you can find that the amount of flow coming into sink T1 is of value T. Here the first value is the residual capacity, second value is the cost. Now since it's a cost network, as we've seen in the algorithm, we have to negate the cost, make it as minus 2 and similar minus 4. Now the total flow to this network is 3, and the actual flow is from T1 S1 to A and A to T1. We go along the reverse edges as we had seen in the max flow algorithm, Fulkerson algorithm. So S1 S to A is actually supplying 3 to the sink, similarly A to T. So this is the path the actual flow goes to. Now to find a negative cost cycle, we only take into account the costs. Now here it is minus 2, here it is minus 4, here it is 1 and 1. So first and foremost we need to find the cycle. The cycle is from T1 to A to S1, S1 to B, and B to T1. Is it negative? It is negative because minus 2 plus minus 4 is minus 6 and 1 plus 1 is 2. The total cost is minus 4. Now why is it we need to remove this kind of a cycle? What this means is, according to residual graph, this is a flow. So what this means is that we can actually uh, go through this cycle one more time instead of uh, letting the goods be at the demand. We actually can have another flow through T1, A1, S1, B1, B again to T1, and we can still reduce the cost by minus 4 because the negative cost actually means a profit. So again, if you are trying to put the flow across, trying to supply goods across this cycle, we are actually making a profit of 4. So you can go on putting flow across the network infinitely. So the actual cost is 18 is not optimal as another flow through edges TAAS, TAAS, SB and BT will reduce the cost by 4 and so on infinitely. So we need to remove a negative cost cycle. This ultimately means that this flow is not optimal. We might need to change the edges from which the flow actually goes to. It's quite obvious here is that because since we are passing only values 3 or 3 units, here it is the cost is 4 and here the cost is 2, and here the cost is only 1 and 1, it would have been better off passing the transporting the goods along these edges and not these edges. So if you remove the negative cost cycle, the flow will change. Now we need to detect and remove a negative cycle. So you use Bellman-Ford algorithm. The input for Bellman-Ford algorithm is a residual graph GF with weights as edge costs. Now the Bellman-Ford algorithm actually finds the shortest path from the source to every other vertex. Here, since we're using the residual graph, we initialize desync to 0. Then we have a loop from I is equal to 1 to number of vertices minus 1. We find the shortest path from the sink. Apart from that, we add a new array pred and we initialize the predecessor edge for every vertex in the shortest path. Then we need to see if any negative cost cycle exists. For that, for every edge, we see if the distance on the sink changes. If it changes, that means the shortest distance changes, that means there's a cycle. Now we initialize the edge which caused this problem into the first element of the array cycle, and then we break, and then we need to find those edges which actually form the cycle. We need to remove all the extraneous edges which are not part of the cycle. So for that we use these two arrays, one of the spread and the other is cycle. We start with the edge which caused the problem. We follow the predecessor edges till we find an edge which is duplicate in the cycle array. Then we start with the first instance of this duplicate edge. All the edges which follow this edge are part of the cycle. The ones prior to them are the external edges, and we remove them and return the only those edges which form the cycle. Now let's take an example. On the left hand side is a graph which is a min cost flow graph. It has a supply node S1, a demand node T1 and multiple two warehouse nodes. There can be multiple supply nodes and multiple demand nodes, but for simplicity I have given only one supply and demand node. Now B is equal to 4 means it can supply 4 units, minus 4 means the demand is 4 units. Here A and B, the B value will be 0. 3, 3 is actually Uij, Cij. Uij is the capacity, Cij is the cost, unit cost. So 3, 3 here means that capacity of this edge is 3 and the flow and the cost is 3. Here 3, 2 is the capacity is 3 and the cost or unit cost is 2 along this edge. Now on the right hand side is a residual graph after running the Fulkerson algorithm. This is a final residual graph which shows the maximum flow along this network is of value 3 plus 1, 4. Now what is the total cost for this maximum flow? So max flow is flow. The total cost, we just multiply the costs with the flow. Cij into Xij. There is 3 into 2 6, 3 into 3 9, 1 into 1 1, plus 1 into 1 7. 1 is equal to 17. So the total cost is 17. If there is no negative cycles, then this is the minimum cost. Now we need to check if there are negative negative cost cycles. So how do we do that? First, we need to create a cost network. How do we create a cost network? For all these reverse edges, we remove the we don't for the cost matrix we don't require the capacities. The capacities will actually be the costs. So for the reverse edges, the residual capacity will be equal to we need to negate the cost, so minus 2. So from T1 to A, the capacity, residual capacity will be minus 2. Here it will be minus 3. Here it will be see, here it will be like 1, and here will be 1, here will be minus 1, here will be minus 1. So this is the cost network, the cost graph. So minus 2, minus 3. Now, are there any negative cost cycles here? We see there's a cycle T1 to A to S1, S1 to B, and B to T1. Does it have a negative cost? All you need to do is add these costs, minus 2 plus minus 3 plus 1 plus 7, 1 plus 1 along these edges in the cycle. So uh, that equals to minus 3. The cycle cost is minus 3. The cycle cost is minus 3. The cycle is from T1 to A, T1 to A to S1, S1 to B, and B to T1. Now we need to remove this negative cost cycle. How do you do that? As per the algorithm, we need to put a flow which is the minimum capacity of any edge. That is how we do it normally in normal Fulkerson. But what is the minimum capacity? Here it is. Now we take the actual capacity. Here is 3 and 3, and while here it is 6 and 7. So the minimum capacity is 3 along this cycle. We only take into account the edges which are there in the cycle. The cycle was, as you've seen, is T A S1 B1 S1 B, and the edges here the minimum capacity is a 3. So what we do is push uh, 3 along these edges only. So if you push 3 along T1 to A, the residual capacity was 3. If we subtract 3, so now it will be forward edge will be 0. There will be another reverse edge from A to T1. So there will be reverse edge A to T1, S1 to A. Similarly, here we are reducing 3 along the forward edge S1 to B. So the residual capacity has become 3, but we have increased the capacity residual by the flow for the reverse edge. So 1 plus 3 is equal to 4. Similarly 4. Now, are there any negative cost cycles? As we see, there are no negative cost cycles here. There are no, in fact there are no there is one cycle from T1 to B, B to S1, S1 to A, A to T1. But if you add the costs, minus 1, minus 1, minus 2, and 6, that that is equal to 4, which is not negative. So there's no negative cost cycle. So this flow which you found is not only maximum, it has the minimum costs. So what is the minimum cost here? Here the cost is 4 plus 4 is equal to 8. The flow is only from S to B and B to T. The flow is 4 here and 4 here is equal to 8. Now what happened is that we removed the flow which was originally we removed the flow which was passing through S to A and A to T, and passed the flow along the less costly path. That is from S to B and B to T. So that happened when we removed the negative cost cycle. So the max flow still remains as 4, 4 here still remains as 4, and the min cost has reduced from 17 to 8.